Kelly wasn't able to make it tonight for meeting chair. I don't know if I saw her in here earlier, but so she asked me earlier this month to take over as meeting chair, and I gave her a challenge saying that she should dye her hair green if I was to come up here into this. So I don't know if she's here with green hair or not, but anyway, so let's get started. We've got a really, really tight, a really packed night tonight. So if we can get this to...
Eric?
Yeah?
It won't work for a second. I'll just advance for you.
Okay, thanks. Alright, so here's tonight's program. We're, like I say, we're really packed. The key feature presentation tonight will be Jim Thompson. He's going to be giving a lecture on observing the sun. For this meeting tonight, I thought I'd put together a bit of a theme, imaging and observing, and something that Paul had talked to me a while ago about, and we had been talking back and forth about, is something called Imager's Corner, where we wanted to present lectures on how to do astrophotography. So I'll talk about that in a bit when we get to that, but we've got a whole segment on that tonight. So let's get right to it. Dave, if you want to come up, give your talk on skies this month. Yep.
Eric, you're up for a while.
Oh, sorry. Yeah, I think there's a few more slides in front of you.
He's new at this.
I thought he was telling me.
And your hair's not even green.
Got members in the news.
So this is actually before we get that, Chris, do we have the monitor working here at all tonight?
Nope.
Okay. So we've had a bunch of new members join this month. Notably, we got Jim Thompson.
Oh.
We'll give him a round of applause for joining. And of course, all the others are back here. And then at the bottom of the screen, we've got everyone else who has joined for this month. So congratulations and thank you to all who have joined. For members in the news here tonight, we've got a few things here. The Carp Star Party that we had for this past month, there was a journalist that came out and asked us if we could take or if we could have our picture taken. So he actually took Mike Malgham's picture beside a family of fine folks looking through his telescope that night. That was in Metro News. This is a presentation from Sharon that made headlines about the observatory and the history behind the observatory here in Ottawa. So she made news there as well too. Congratulations, Sharon. And then this one right here is this is Pat Brown. She caught something in a previous article in Sky and Telescope. Wrote in, and they published her her paragraph right there. So congratulations, Pat. All right, now it's Dave's turn.
Well, good evening, folks. We have 354 slides to go, so I can move quickly. Just kidding. It's not that bad. Okay, so let's take a look at the moon phases for the month. So a week tonight is the full moon in June. And you can see for our next star party in June the 30th, it won't be too bad. Got one comet here, Comet C 2015 V2 Johnson, magnitude plus 6.5, visible in a decent scope, and it's going to be visible for the next little while. So, going quickly through the planets, Mercury is not really visible this month, it's too close to the Sun. Venus, we have the greatest western elongation on June the 3rd, and Mars is visible in the early evening, the first half of the month, at which point it will disappear for a while. Jupiter is visible all month, it's been nice and clear, and will remain so. And Saturn's now rising at a reasonable time, and will be visible all month in the evenings. Uranus is visible in the early morning. Neptune is visible in the early morning all month as well. International Space Station, the best viewing date is June the 8th, which is this Thursday. It rises almost directly overhead, 86 degrees, and it's at a reasonable time, so 9:30 in the evening. There's a picture of where it's going across the sky. And there's your cartoon for the month. Thank you.
Okay, next we have Al Scott with his 10-minute astronomy news.
Thank you. So welcome. This evening I've got 3 news items for you. Honestly, it was difficult to choose what to present. There's so much interesting news out there right now. So I kind of picked a theme for this month about where's the flux. So 3 stories about missing flux. First one is regarding the cosmic microwave background. Many of you know that in all directions from the sky there's a microwave signal coming towards us, and scientists believe this is remnant echoes of a time when the universe was denser and hotter in its early history, and it's been redshifted by the expansion of the universe. Well, people have mapped this this background radiation all across the sky, and they found that there's slight deviations from a uniform temperature. Some places are a little bit warmer, some places are a little bit colder, just as you might expect if this was a roiling plasma in the early universe. However, there seems to be one particularly cold spot which isn't well described by the theory of the plasma and what we know of physics, and it seems anomalous. So astronomers thought, well, why is this? Well, there are many things that could cause a potential cold spot or hot spot, and they're to do with foreground objects. Effectively, if you have large galaxy clusters, you can get hot spots, and if you have large voids between you and the signal, you can have cold spots as the light is gravitationally shifted by going through these objects. So what astronomers did was they said, okay, here's a cold spot. This must represent a huge foreground void of galaxies larger than any we've ever known. So they went and they actually took some telescope observations and measured the density of galaxies between us and that direction of the sky. And they compared it to some galaxies in a different portion of the sky that didn't have a cold spot to get a normalization. So here are the galaxies between us and this microwave distance, and the distances are derived from redshifts through the Hubble constant. And here is towards the cold spot, and what we see is there is no void. So this was a surprise to the astronomers who did this research. Effectively, they were expecting to find a void. So they surveyed the redshifts of 7,000 galaxies, harvested 300 at a time using a spectrograph on the Anglo-Australian telescope. So if there's really no supervoid that explains this cold spot, simulations from what we know of physics give us a probability of only 2% that such a large cold spot could otherwise exist by chance, which is uncomfortably low. It could just be a fluke that this happened. I mean, we only have one universe as a reference point, so we don't have a statistical sampling that we can go from in universes. The discovery could, however, point to other more exotic physics and cosmology, perhaps looking at collisions between early universes in the multiverse, although I have no idea how they might test that. So we're looking forward to an explosion of theoretical speculation as to what may be causing this, if it's not just a 2% random fluke. So keep your eyes peeled, and it's interesting that the early universe physics and cosmology is expanding through observational studies now, rather than just philosophy. The second one is a topic that I've talked about before. It's Tabby's star, or the WTF star. This is one of the Kepler stars that had some very anomalous dimming events that didn't seem to follow any sort of a regular pattern. So a recent model has been proposed by a group of astronomers suggesting that maybe what we're seeing can be explained by a natural phenomenon. As you may recall, some of the explanations for this range from alien intelligences assembling Dyson spheres around the star, clusters of comets disintegrating in orbit around the star, various more exotic explanations. But what we see here is the actual data. So the data started May 1st, 2009, and we saw these anomalous dips in brightness of the star, and then a huge dip May 4th, several days long, asymmetric, and then nothing, and then some more dips, and another huge dip, but very narrow, and some other small dips. So what the astronomers now think might be occurring, and this is a prediction, this hasn't been verified, is that perhaps what we're seeing is a Jupiter-sized planet with a large ring system here, and the ring system is tilted, and that's what's giving us this asymmetric dimming as this planet moves across the star, with two swarms of Trojan asteroids at the Trojan points. We know there are stable gravitational points on a planet's orbit, and they're called Trojan points, and there are Jupiter in our own solar system has a collection of Trojan asteroids that both precede it and trail it on its orbit. So if this planet were to be a large Jupiter-sized planet, based on the depth and the size of this, they estimate 4 or 5 Jupiter masses at a distance of about 6 astronomical units from the primary with the 12-year orbit. This is roughly where you would expect the Trojan swarms to occur. And if that's correct, then we just missed the first one when the observations started. But now we can predict when we should be able to see other dimmings, and there was actually just a recent dimming a couple weeks ago of a low magnitude. So, but to actually get this sort of a dip, you need some very strong clustering in the Trojan asteroids. So it's not clear whether or not that's feasible based on our knowledge of the dynamics of these things, but it's an interesting proposal and it's testable. So we'll keep watching. The most recent dimming a couple weeks ago, all the telescopes that were available pointed over there, tried to take some spectroscopy, tried to see if there's any signal, any color change associated with this. So stay tuned, there's probably going to be some papers coming out looking at the latest dip. And everyone's going to keep looking at this to see whether this prediction comes true. And my last item, this is really cool. N6946-BH1 was a red giant star, estimated at 25 solar masses, and one of several supernova candidates that was being monitored by the Large Binocular Telescope. This luminous star appeared to dim in visible wavelengths while brightening in the infrared from about 2005 to 2008. In 2009, it underwent a transient brightening event for several months, peaking around 1 million solar luminosities, and then it vanished. Observations in 2015 showed nothing at the site, except a slight cooling infrared shadow, basically, of cooling dust. Amateur observations of NGC 6946 nearby from 2009 with a limiting magnitude of 18.7 were used to constrain the timing of the event. So what happened? Researchers considered a variety of processes that might make it look like the star had vanished. For example, dust being expelled, pushed out from the star. Most of these can be disproved from the infrared observations. That sort of injection of a large amount of material would also make the gas and dust quite energetic, and they should be easy to spot. Careful follow-ups by Hubble and Spitzer confirmed that there was really nothing there. So what may have happened? Stars that reach the end of their life, supernova candidates, are burning their nuclear fuel fast. And when they run out of nuclear fuel, one of two things are supposed to happen. If the star isn't that massive, it burns out into a carbon-rich remnant called the white dwarf. If it's big enough, the star is expected to end with a bang, a supernova explosion, where it blows off its outer shell, this core collapses into perhaps a neutron star, and then perhaps into a black hole. Well, when we look around at supernova remnants and look back for the progenitor stars, no one's ever found a supernova with a progenitor greater than 18 solar masses. which is troubling because we know those stars are out there and we expect them to go supernova. In fact, there's evidence that massive stars are formed more frequently than the rate of supernova that we observe suggests. So, what's going on? Recently, the Laser Interferometry Gravity Observatory measured black holes coalescing, and the black hole masses were greater than 18 solar masses. They were 30 plus solar masses. So we know that these kind of super solar black holes exist, but we don't know how they form. Or we haven't seen them being formed in supernova events. So what astronomers think is happening is that these supermassive black holes collapse directly into a black hole without a supernova explosion. And this is the first direct evidence for that process. Astronomers have been searching for this in this particular study, and they found a candidate here that just disappeared. So if anyone happened to have been observing NGC 6946 in the last decade, you might have some interesting observations to share with this team. Future measurements of X-ray emissions from that site would confirm the source, the possibility that there's a very compact, highly compact source that may be swallowing up gas in its neighborhood. And further infrared emission measurements will continue to be taken to continue to verify that there's nothing there. But this is an interesting discovery, and it ties into the most recent observations from the Interferometric Gravitational Observatory that another pair of black holes has been discovered just this last month, and I didn't get time to put it in here, we're a little bit rushed for time, but it also had supermassive not supermassive black holes, but large, greater than 18 solar mass black holes that may have been formed through the same method. So a very interesting discovery, and hopefully we'll follow up and learn more about this in coming years. Thank you.
Thanks, Al. That's very interesting. Okay, so now we're at this Imager's Corner segment, we're calling this. So let me just introduce this slide, because I feel we'll be using this in the future for other Imager Corners presentations. The idea behind this is that we've heard from our members that you've seen a bunch of people come up and show pictures, but there hasn't been a whole lot of explaining how we get those pictures. And if there has been, it's been quite advanced. So Paul and I had this conversation earlier about how we'd like to actually start a series where the idea behind this is not that we're giving a full presentation, but that we're giving segments of, or lessons, as you will, in terms of, like, tonight we're going to have the beginning lessons of how you get started, and then next time at a future date we're going to have, you know, say lesson 2, and then lesson 3 we're going to get more and more advanced and into more details as time goes on. So for this slide here, I thought that I'd put together some screen captures. In the left here, this is an image of a Celestron 11-inch telescope, and this instrument is capable of taking pictures such as this fireworks galaxy, I believe that is right there. And that shot is is Photoshop. The one down here shows some time-lapse image processing in Lightroom. The one up here, this is PixInsight, showing its multiple windows that can be opened at a time. We have Registax here for processing Jupiter, and then some equipment down here for taking time lapses. This is actually, it's sort of hard to see, but it's a slider that's 2 meters long, and then this gear right here, it rotates and pans and tilts the camera as time goes on. So I'll be giving the first lecture here tonight on time-lapse photography. I'd ask that if we have questions, since we're so tight on time tonight, the three of us that are going to be giving presentations in this section here, Paul, Taras, and myself, we'll gladly field your questions at break or afterwards. This is part of the reason why we're doing this. It's just that we're so tight for time tonight that we want to move quickly. So what am I going to talk about tonight? Sorry, hold on a second here. Yep. So I want to get you guys started off on which equipment you want to select when you're thinking of doing a time lapse. I'll walk you through the settings that you need to set up on your camera and on your intervalometer as well too. And then choosing a scene sometimes it's different than taking just a regular still image. And then I'll walk you through a checklist of items that you want to make sure, or things that you do along the way to make sure that everything lines up. So what exactly is time-lapse photography? It's essentially time manipulation, right? So you're playing back the video at a different frequency than you're capturing it. So you might take a picture every, say, 30 seconds, and then when you play it back, if you've, say, taken 1,500 images, you play those back at 30 frames per second. So what that allows you to do, it allows you to visualize movement that you otherwise wouldn't. For instance, the other night, I don't know how many of you saw this storm that whipped through the Ottawa area. Pretty ferocious storm. A time-lapse would have captured that, as billowing clouds and the rainbow appearing and lightning going all over the place. In fact, actually, when I took that picture, lightning hit pretty close to me, and I kind of scrambled back to the car. Big open field. That's right near Gary's house, which I also took this picture right here down there with the windmill. And right behind me, that's the sunset. So you can imagine how things were pretty dynamic. And then, of course, a flower that's blooming. You don't always appreciate until you see in the time lapse what's actually happening. It's kind of like watching fingernails grow, right? So, first step, you want to choose a good solid tripod. I like to use a tripod that has a ball head, and that allows me to very precisely frame the scene without having to use a bunch of different knobs. So obviously in this case a large ball head is going to be best. You want to choose a tripod as well too that's nice and light. So carbon fiber tripods are great because, let's face it, sometimes you have to hike several kilometers to get to that spot that's going to look really, really nice. Not so much if you're in the middle of the field, it's not all that hard to carry your equipment, but if you're scaling a mountain, it might be, right? So you want to have stuff that's really light. When you have a really light tripod, though, it's going to sway in the wind and it's going to resonate, which is really bad because you'll see jitter in the time-lapse afterwards. So one of the tricks I like to do is I hang a bag of rocks from a hook on the tripod, or if it's particularly in a hairy situation, I'll actually tie it down with ropes from that hook, and then that makes it nice and solid. Because one of the things I tell people with time-lapse video is that you cannot have any motion whatsoever in your camera. If that tripod were to move just a slight bit, you'd see that so easily in the time-lapse video afterwards, where everything just shifts, and then from that point on, it's not the same exact frame. So it depends on your focal length as well too. A wider focal length will be a little bit more forgiving, but it definitely matters. And then to offset or not to offset, this is all about, sorry, I'm just looking behind me here. This picture right here shows how the tripod that I use allows the center column to come out of the tripod, and then you can push it over to the side. So this is really handy if you want to have a really close-up time-lapse sequence where you need to get the camera really close to the object, but the tripod legs might get in the way or such. So now the next step you want to pick is a camera to do this. And pretty much every camera that can have the ability to do repeated shots will be able to work for this. You want to be able to set it up into manual mode so that you have full control of the camera. A camera that has manual ISO is going to be a lot more manageable as well too. So you can do this with point-and-shoot cameras, but an SLR is definitely a lot easier. And the reason is because you can interchange the lens. The SLR lenses, typically, if you have a manual lens, you can have manual focus, manual aperture, and you can avoid flicker that way. They have large image sensors and they're very sensitive to low light conditions. And they allow you to capture the image data in its raw format, and that's really important because if you were to save your images as a JPEG, later on when you go to work on them, you're going to run into problems. And some of them even include intervalometers. The Nikon ones are good for that. The Canon ones don't always have them, although Andrew Brown has been using something called Magic Lantern, which allows you to then essentially load a third-party firmware onto the camera, allowing you to give or to have a built-in intervalometer. As lenses go, I mean, you can use a variety of lenses, right? A 14mm lens is going to give you a really wide field of view. I like to use it when I have a really large Milky Way expanse that I want to capture. Kind of gives you it's not exactly the same, but it's sort of like that spacewalk feeling, except for you're on ground, right? I mean, it gives you that big perspective. Whereas a telephoto lens will be able to capture something in the far distance. It'll work great for a moonrise. It also works pretty good for aurora sometimes, surprisingly. A lot of times you want to use, say, a 24mm lens for an aurora, but if you're that much closer, per se, or your field of view is narrow, sometimes you can focus on individual structures in the aurora, which sometimes works out well. The most important thing about the lens is that it's fast, and what that means is that the aperture is really wide compared to its focal length. I can't stress that enough. When I started out doing time-lapse photography, I was using a lens that was an f4 lens, and I could take a 30-second image of the Milky Way. I'd probably have to use ISO 6400, and in doing that, I'd introduce all sorts of noise to the image because the sensor is really warm during summer, at least. Having a lens that's really fast, but these two lenses right here that I've got, this is a 14mm lens, this is a 24mm lens. This 24 they're both Rokinon lenses. They're both manual focus, manual aperture. And these are the two lenses that I use the very most. You can't use autofocus at night anyways, right? So these two lenses have Canon equivalents that are worth 10 times their price. And the Canons are great when you're focusing on stuff during the daytime. They'll be sharp across their whole range of how close everything is to the camera. These particular lenses work the very best at infinity focus. So essentially for nighttime photography with stars, that's perfect, right? So these actually outperform some of the Canon lenses that are 10 times more expensive. They have a manual aperture ring, which is really key for this. With a lens that doesn't have a manual aperture ring, you can't set and fix the aperture to what it will stop down to every picture. So essentially there's a little bit of error every single time the picture is taken, and that little bit of error, and it might be really small, will present itself as flicker later on when you're trying to put the image back together. One image will be slightly brighter, the next image will be slightly darker. So this helps out a lot. So it's funny. You'd think, well, a cheap, inexpensive lens is not going to be good. In this case, way better than the Canon equivalents. So to get started, you want to use an intervalometer, like I said. These are two third-party intervalometers that I use. And essentially, you have the ability to set up a timer for them so that you can delay the initial start of the project. You can set the interval time at which the camera triggers, and then it waits that interval again before it triggers again. And then you can set the exposure time. Now, if you're going to set the exposure time, you need to also set on your camera, you have to set it up to bulb. Then the intervalometer itself sends the trigger signal to the camera, and it will, but the setting of the time on the intervalometer will then tell the camera how long. Otherwise, you can set it up for, say, a 10-second exposure, but if your camera is set up for a 5-second exposure, it'll send that first trigger to the camera, but then the camera automatically just takes a 5-second picture, and you'll be left wondering, well, just why is it not working exactly? So it's important to put it onto bulb mode. On some cameras, this will be found under the manual mode. You'll just adjust the shutter speed, and then you'll eventually get to bulb. On other cameras, you'll actually have on the dial a special bulb mode. The last one is the frames, and this just allows you to take a range of images. Maybe you only want to take 10 images, maybe you want to take more. In the case of time-lapse, you want to go long. When I first started doing this, I'd take 200 or 300 images, and then I'd try to stretch it over time, and it would be very choppy. These days I take 1,500 pictures. Sometimes I take as many as 3,600 pictures. The idea being that you can overtake pictures, and you can always speed the video up, and it will always be smooth if you speed it up, but you can't slow it down past a certain point because it gets choppy. So when you consider you want to play it back at about 30 frames per second, it gives you an idea how long you want your video to be. If you take, say, 1,582 pictures, it'll be something like 52.7 seconds long. I'll have that later. By the way, there's a test at the end of this. I'm trying to see if you're paying attention. Do you think I'm joking? All right. Who caught the test right there? All right, so choosing a scene. The main difference between time-lapse photography and still photography is that when I aim my camera this way, and I'm trying to take a picture of the Milky Way, it's not going to be there in 8 hours or 6 hours, right? It's going to be tilted, it's going to be across the sky by a certain amount. So you have to calculate, and this gets into motion, which I'm going to get to in a later segment or later lesson. But you have to picture, okay, so where is it going to be at the end? And it's still just as important to frame the object in time-lapse. Just because it's video doesn't mean you don't have to frame it. And I try to consider that every frame I'd want to use on its own. So I try to set up the beginning and the end frames, and the stuff in between, you sort of can imagine it. It's kind of tough sometimes. But so what I typically do is I say, okay, the Milky Way is here. I'm going to look that way, and I'm going to see, or at least on my planetarium program, I know that the Milky Way is going to be over here at time X, right? So then on my planetarium program, I look and say, okay, right now, this particular bright star is right here. So then I frame my picture based on that star. And then, of course, at that time, the Milky Way is going to be in that area. So that makes it a little easier. But the main thing you're always thinking about here is that there are foreground static elements and there's dynamic background elements. The foreground objects are going to stay there the whole time, so you really want to make sure that whatever you have in the scene is going to look great. And for instance, the background image of this slide right here is a bunch of trees that are silhouetting the background Milky Way. So the Milky Way is highlighted. But sometimes you have something in the foreground that you actually want to emphasize. So what I'll do is I'll take along my headlight and I'll do what's called light painting. And I'll light the scene while the shutter is open. And that can be a bit of a challenge. I'll get to that in a future lesson as well too. But you just have to get the right balance of lighting for how long the shutter is open for. So I've covered here where is the Milky Way going to be in 6 hours. Where is it going to be on the next slide? And if you've got the trick, where was it on the first slide, right? You go back and forth. So anyways, let's try this out. I've put together a checklist, and these are the basic things. I'm going to add to this in future lessons because there's a few more things on here, but this is the basics. So essentially, you need your camera, and you need the tripod. Of course, you want a charged battery that's not going to run out on you in the middle of the night. And you need a full camera card, because there's nothing worse than either of those running out in the middle of the night. I've had aurora shots where I'm 2 hours west of the city here, and it just starts flaring up like crazy, and the battery dies. And of course, I could just put in a new battery, except for that the camera, like I said earlier, if you touch it, you're never going to get it back to the same spot, and then what's the point? Because you'll be watching, the auroras going and everything, and all of a sudden, and it shifts. So So what you want to do is you want to set your camera to manual mode and enable the raw image capture. ISO, set it manually. Don't let your camera do what's called automatic ISO, because there's going to be subtle shifts in the noise, and it's not so apparent on any individual picture, but in playback, I mean, there's often things that you just don't see until you see it in video playback. I've taken shots where I look at them later and she's like, and I think to myself, geez, there was auroras that night. Like, I would have never seen that on any individual exposure. So then you want to set the longest possible exposure that you can given the aperture that you're going to use. And this 500 over FL rule, focal length, is essentially how long you can go before the stars are going to trail. So you divide 500 by your focal length, and that will give you the time in seconds that you can take before the stars are going to no longer be round.
So for 500 millimeter lens, you expose for 1 whole second?
Pretty much. Yep. So in that case, you're going to want to have a pretty high ISO. The problem with that, though, is the noise. Right? So it's always a balance. And I find with my 24 millimeter lens, I use a Canon 6D. I tend to keep it to about 10 to 15 seconds. I probably can go a bit longer than that, but I find that it exposes properly there. I never like to go above ISO 3200. I've done it 6400 before, but then the noise becomes too much, and then it kind of ruins the shot, because it then looks really speckled and it looks like you've taken a shot in the dark. So then you want to also open up the aperture as much as you can, right? That 24 millimeter lens I have, I can shoot it at f1.4, so that drastically reduces the time that I need to take every exposure, and that's really great because then you don't have to bump the ISO up. It's kind of one or the other, right? You bump the ISO up, you can take the aperture, right, the aperture goes up as well too, right? Smaller opening. So, you know, essentially, if you don't have a lens that can go really wide, then you need a camera that has very low noise, and you can bump the ISO really high. When you have both, it makes it really easy to take. I mean, you can get down to like 5-second exposures, and for auroras, that's great because then you can capture all the individual motions of the ribbons moving back and forth. Whereas a 30-second exposure, it all gets blurred. With the Milky Way, it's a little more forgiving.
Eric, excuse me, on the last line there, with the twist, lens twist.
Oh, sorry. Yeah, that's all. Thank you. That's important. Manual aperture rings don't need this, but say you are using a Canon lens that has an automatic aperture. There's a technique by which you go to remove the lens ever so slightly, and it just disconnects the electrical contacts from the camera, so the camera can't control the aperture. So essentially, you program it for that, and then expose one picture, and while it's stopped down, you turn the lens and detach it from the camera. Now, warning about this, be really careful, because if you do it too much, the lens can pop off, and you don't want to have that happening. Again, that's one of the reasons why I like these manual lenses, so you don't have to worry about that. Okay, so you want to turn autofocus off after you focus it. This is important because when you go to hit the shutter button later on, if you only depress it a little bit and autofocus is on, well, there goes your careful focus, right? The camera will just spin back and forth in its range. Stabilizer, you want to turn that off too, because that will shake the lens. You can always see that in a long telephoto lens when you go to take video. It's a bit of a shaking in the image. So then of course you want to compose and frame your image, like I was saying earlier, and then take a test image. Check the histogram after the end of that. The histogram is you have the lowest brightness levels on the left, and you have the highest brightness levels on the right. And it's a measure of how many pixels under each of the different values of brightness, if you will, are in the image. So what you want to do is you don't want to have any dead space on the left. You want to have your histogram right up against the left so that you're getting as much dynamic range, I guess you could call it, as possible. If you bring it too far off the left, then you don't have enough exposure. If you bring it too far off the right, you've got too much exposure and the brighter part of your images are going to start to clip. So then with the intervalometer, you want to set it to twice the length of your exposure. This doesn't always play into it. Sometimes if you have, say, 5-second exposures or 15-second exposures, you can take like 5 seconds to download the image and then start it right back up. And sometimes that's important, right? Sometimes you want to capture everything. If you're trying to get meteors or whatever else event happens in the sky, especially like auroras, you want every single frame possible. You want to capture that whole thing. The only time that you want to have the camera down is the shutter closed is when you're downloading the image to the card. Typically takes about 2 to 3 seconds on fast SLR. But where this comes into play is if you do it in the daytime. In cinematography, there's this concept where to make things smooth so that, what just happened there? Okay. To make things smooth, I'll exaggerate here a little bit, but suppose you take, I don't know, 30 seconds as the interval, and then your shutter speed is like 1/30th of a second. You're going to capture that one short period of time, and then you're going to wait the rest of the time doing nothing. So you're going to compose your time lapse of individual, bursts of shutter open and then close most of the time. And so when you play it back, a keen eye will see that. It just won't be very smooth. So in that case, what you would want to do is put on a neutral density filter so that you reduce the amount of light coming in. In the daytime, there's plenty of light anyways for that, and then take a 15-second image. So you get a bit of blur in your image, but then because the interval is 30 seconds, you bring a bit of that motion into the time lapse and things seem a bit smoother. So again, it depends on your subject, but this is a trick that's been used in video photography for a while. So where were we here now? This is part 2? All right. So then start the intervalometer. And the most important part is don't touch the camera. I don't know how many times I've been curious, right? It's like, I wonder where is it at during the sequence? And what does the exposure look like? I'm going to check it. And of course, I'm taking 10-second long images, and I figure, well, I'm fast. I can do it in 10 seconds. I'll miss one frame. And later on, I see it. That presents itself as a little small jitter. And so to somebody who's seeing the video for the first time and has not seen this stuff before, they think, the computer's slow, right? I look at that and I say, the person checked this video, So, yeah, so that's all I can say about that. So this is a time lapse that I took down in the Winter Star Party. I've got motion here on this one. I set up my rail so that it moved around this tree structure that I also spent a good half an hour trying to figure out different positions and stuff. I had a bit of fun with that, but with that. The light going across in the back there, that's a cruise ship. We're looking south in the Florida Keys here. And this basically goes on and it shows the Winter Star Party as it was progressing. These guys, some of them had like 24 or 25-inch Dobsonians. The guys behind us had like 36-inch Dobsonian telescopes. So I just thought I'd give you this example. Many of you have seen some of the time-lapse images or videos that I've shown before, but to those who have not, this is what I do. And that's the end of my presentation. I hope And so the next up here is called. And one of the things I wanted to say as well too, when I was introducing this concept of Imager's Corner, is that we're doing it tonight, but we'd like to keep this going, right? So any of you out there who do imaging, I mean, it'd be great. Let's keep the flame going here, and keep on giving tutorials on all these on topics, because our members really are interested in this stuff, and they keep on telling us, hey, we want to know more. So with that, I'll hand the floor over to Paul Cloninger. He's going to talk to us about the essentially the beginnings of trying to do astrophotography and setting up your telescope and what kind of cameras you want to. So it'll sort of complement my lecture here on cameras, because he's going to talk about some of the stuff that I didn't mention. All right, here you go, Paul.
Thanks, Eric. Well, good evening, everybody. Yes, as Eric mentioned, this is an idea we've been batting around, especially in light of the survey results that we recently received that showed that there was a fair bit of interest in astrophotography amongst the members, folks that haven't tried it before but are interested, and other folks that give it a hand perhaps and maybe want to advance what they've done there. So this is, yes, as Eric mentioned, this is a set that we've developed that we hope to be an ongoing thing, and we encourage anybody that does imaging that has techniques and things that they'd like to share, that this is something that we can pass on to the full membership. We're also planning a set of lectures, and Mike Mogadam is actually organizing that, where we'll do special lectures for the members that will give us a bit more time. They'll be at venues like libraries and such, where we can get into astrophotography and have a bit more time to play with. Certainly, our segments here are going to be very short generally, and as such, they're not intended to be a full discussion on things like doing astrophotography from A to Z. I also give a course on this at SPAO, which runs for about 16 hours in total of classroom sessions. So as you can see, I'm a bit more limited in 10 minutes with what I can say. And Eric, I will definitely try to keep this to 10 minutes. So, unlike other people I know. All right. So basically, what I'm doing here, this is the first segment in what I hope to be an ongoing thing over the next number of months. And essentially, I'm going to just talk about super basic stuff. If you're interested at all about in getting into astrophotography, whether you're doing auroras or you want to catch meteor showers, do nice shots of the Milky Way, especially when it's prominent in the summer and the fall months there. If you want to do lunar photography, if you're interested in doing eclipse photography, or if you want to look at things like distant galaxies and such, all these things start from the same beginning, and that's to know your camera. And that's what I'll look at in my first segment here. Little bit of a digression here. This is an image of NGC 6946, the galaxy that Al was actually talking about. And 19 days ago, this galaxy, I thought I'd put this into my presentation here, so I was originally going to do this in the observer's images, but we are pressed for time tonight. So I just want to show you this. 19 days ago, a supernova was photographed in this galaxy by Patrick Wiggins of the United States. And it seems as though he caught it within a day or two at the most of the initial explosion. And I imaged this galaxy last year, just because it's an interesting galaxy. It's not a super deep exposure of that galaxy, and something I wanted to get back to, but I was fortunate that I had this image from last year, shot it about 14 months ago, and that is the galaxy. It's about 22 million light years away in the constellation of Cygnus. And so when I heard about this supernova last weekend, while other folks were having the good fortune of seeing an aurora, I was busy with my nose in my observatory photographing this galaxy again to try to catch this supernova. And did catch it, integrated the data with my earlier shots, and there's the supernova, right there. So this is, my shot came about 2 weeks after the initial discovery, and even at that point in time, it was still at, that supernova was still at magnitude 12.8. So this is a very active galaxy. It's also called the Fireworks Galaxy for good reason. There's been about 10 supernovas discovered in this galaxy in the last century, which is well above the average rate for galaxies like this. So at any rate, back to the discussion there, whether you're doing this type of photography or just
plain simple, you just want to check out the sky and shoot various things like meteor showers and auroras, it all boils down to the camera that you choose. And today we have a lot of cameras to choose from. We have a plethora of them. Is this laser working, Chris? Or will I totally screw things up? Oh, it is working. Wonderful. Okay, so we have, point and shoots, video cameras, DSLRs, mirrorless cameras, dedicated video cameras. We even have cell phones. When I give my course at SPO, and also when I teach up at Algonquin College, I always have my students on the field session bringing out their iPhones, and they want to put their iPhones to the telescope and capture a picture. The bottom line is that today's cameras are awesome. Like, compared to what we had to deal with in the film days, it's an entirely different world. They're very capable cameras. Some of them are, they're reasonably priced. You can do a lot of cool stuff with these cameras. But for astrophotography, it's really probably the most challenging form of imaging that you can do, because the images or most of the objects that we deal with are very faint, and most of the time they're up at night. So unlike normal photography, taking pictures of the kids in front of, a monument or something like that, it doesn't work for astrophotography. You've got to be in a different mindset, and you've got to have a camera that's capable of allowing you to make adjustments. Eric alluded to this certainly, and I'll just reiterate some of these things that are important in terms of catching any type of astrophotography. So as I mentioned, we have a lot of cameras that are dedicated to, these are general use cameras dedicated to general purpose photography, and things like the specialized video cameras or astronomical CCD cameras. That's a different kettle of fish for more advanced photography. We'll get into this in later sessions there, but for a beginning session, I'm going to focus on using DSLRs. These and the mirrorless cameras, these are relatively new, but they share some very common characteristics. These cameras are the most versatile in terms of giving you the flexibility to make the adjustments you need to capture astrophotographs. So my discussion will focus on DSLRs, but it will generally apply to mirrorless cameras as well, and not so much to things like the point and shoots and video cameras. Things like point and shoots again, and even cell phone cameras, like I say, they're very capable cameras, but most of them don't allow you any kind of manual settings, or they're very limited and too limited actually for our purposes. It's really only the DSLRs and the mirrorless cameras that give you full flexibility to exercise what the camera's physical makeup is capable of delivering. All right. One of the big advantages of DSLRs and mirrorless cameras is that they have interchangeable lenses. The lenses are important because, again, we're dealing with faint objects here, so the idea is to drink in as much light as possible in the exposure time that you choose to use. As you see, when you look at things like point and shoots or the camera lens on your cell phone camera, for instance, these are very tiny lenses. And again, they were engineered with the idea of taking pictures in daytime and taking selfies. Ask Pierre and Justin, they've mastered that type of photography. But for astrophotography, we need light. We need to drink in light. Unless you're shooting things like filtered solar images, excuse me, or the moon, almost all the other objects that we have to deal with are exceedingly light and are exceedingly faint and require longer exposures. We need to drink in the light. So having an array of lenses is significant going forward, because they allow you to capture that light with a fast lens and therefore minimize your exposures. The second thing that you'll need if you want to try this is a tripod. And Eric mentioned tripods, so I won't spend too much time on this, but also, you can see the tripods come in many different flavors. What you want is something that's stable. If you're going to take your DSLR and you've got a honking big telephoto lens that you want to try, if your tripod is too lightweight, if the capacity isn't there, it's going to be flimsy, it's going to be difficult to frame your shot, and if there's any kind of breeze or anything like that, things can move around. So you want something that's solid. You want to look at a tripod that is, hopefully at least double the weight capacity of the camera and lens combinations that you intend to put on it. That'll give you some nice flexibility. And as Eric mentioned, there are different types of heads that come with these things, like the ball heads. I quite like these myself. You can have your basic video type of heads where you can pan and tilt, and you can even use things like gorilla pods if you're in a pinch there, especially if you're doing wide angle stuff there. But again, very limited in terms of being able to adjust the camera once you've set things up. But tripod is a necessity for this. So first you've got your camera. Now you've got your tripod. The other thing you'll need is a shutter release. A lot of cameras have self-timers. They're okay, but they're limited in their use, and they certainly make things less flexible for you. So you can get very simple shutter releases like this mechanical one. Basically just jacks into the port in your camera and allows you to fire off shots without actually physically touching the camera itself. You're just basically clicking. And that's not bad for doing still shots and timing them. I mean, these things are inexpensive. You can get these for a few tens of dollars. But if you're doing things like time lapses especially, the last thing you want to do, especially if you're doing Eric time lapses, is 1,500 shots like this. I guarantee you're going to get numb thumb after that. So an intervalometer, as you can see attached to the camera here, same thing, it jacks into the camera's port. It's got the smarts to do the photography or to do the exposures that you want. As Eric mentioned, you can set the length of the exposure, you can set how many images you want, you can set the duration of time in between. And once you've got that in setting made, all you do is hit the start button, it's hands off, and you can let the camera do its thing. So it's important to, one thing I should have mentioned when I was talking about cameras, is that, again, one of the significant advantages of DSLRs and of mirrorless cameras is that bulb setting that Eric mentioned. For those of you not familiar with that, most DSLRs have a range of exposures that you can select from maybe like an 8,000th of a second up to 30 seconds at various intervals. Beyond 30 seconds, though, you need a setting called B, or for bulb, this is from the old days, that will allow you to go really any length you want beyond 30 seconds. So your camera has to have that for some of the longer duration stuff that we like to image in the night sky. You can also get wireless rigs like this. You can get wireless, small Wi-Fi rigs there that allow you to set the camera up. You can also get things like the infrared remotes there. These I don't recommend as much because often in astrophotography, when your camera is pointed at a part of the sky there, some of these rigs require line of sight between the remote unit and the front of your camera because they are IR based, and so you basically kind of have to move the unit in front of the camera, which is not a great idea. So I wouldn't recommend these. At the very minimum, those are ideal. Again, shop around because this intervalometer is from a third party. The Canon intervalometer that's virtually identical to this in form and function is about $300. You can pick up one of these third-party devices on the web for $40, and they do exactly the same thing. I've got a couple of them, and no failures ever, and they work beautifully. So shutter release is important. So you've got your camera, you've got your tripod, and you've got your shutter release. The last thing, and again, this is, I'll call it optional for now, but if you wind up getting into this, it's not optional at all, and that's a dew heater strap. In our climate, especially in the spring and the fall, we tend to get damp nights. And when you're using a wide-angle lens, as Eric was mentioning for doing time lapses, and for this purpose, where we're just doing very general shots, you've got a lot of glass exposed to the cool air in the evening. And if the humidity is high, that humidity will condense on your lens in just a few minutes sometimes. It's amazing how quickly dew will form on that. So to avoid that, what we do is we use dew heaters. These are essentially straps. you can see wrapped around the front of the lens here. These are straps that have a low current flowing through them. There's a heating wire that goes through this configuration, powered by a 12-volt battery. The battery itself typically runs into a control circuit, which allows you to set how much heating you actually apply to the dew strap. It also allows you to jack in multiple dew straps if you're running multiple cameras doing different images on the same night. So that's kind of handy. Technically, you don't really need this. If you're good with a soldering gun, you can just make up your own. You can get a dew strap like this for $30 to $40, and you can make up an adapter that will allow you to connect it directly to a 12-volt power supply. The only problem with that is that you can't regulate it. It's either on or it's either full on or full off. So the controllers are nice, but they're pricey items. They're around $150 to $200 for that. But really a good piece of kit to use because, as I say, it can ruin your session. If you've driven out somewhere to try your hand like at FLO or something like that and try your hand at astrophotography, and 10 minutes into it, you're wondering why nothing looks sharp. You look at your lens and it's like dripping. But dude, that's really frustrating. So yeah, worthy investment. All right, so the lesson itself, and I'm going to step through this really quickly. What I'm going to do is, I'm not going to spend a whole lot of time on this because I am trying to keep to my 10 minutes. For those of you that are interested in following us up, if you haven't done imaging before, send me an email, paul.coninger@yahoo.ca. I'll send you the JPEGs of these next few slides that have the steps on them, right? So that you can, and you can also pull it off the video. Are we recording it? Oh, we are recording video tonight. Okay. So when Eric has the video compiled, it'll also be available up on its usual place on our site there. But if you want a head start on this, like I said, send me an email. I'll send you the list of these JPEGs and you can follow through the steps as soon as you get an opportunity. So first thing about doing any type of astrophotography, as I mentioned, it doesn't matter what your end goal is to learn your camera. One of the things that I found when teaching my course at SPOW is that, I see guys investing like thousands of dollars in high-end cameras and they've never taken that off auto. And I'm going, okay, well that's going to change. I'm going to change that for you right now. So if you've got a camera, if you've got a DSLR, first rule of thumb is to experiment. Check out what you've got. Check out what your camera is capable of delivering. You need to be able to set things up fully manually. You need to be able to set your exposure time, the lens aperture, in other words, how wide or how closed up the lens is, setting the ISO level, and focusing. Forget about autofocus. It doesn't work at night, with the exception of very, very few objects like perhaps the moon. But typically, it's a very manual process. There are things that I won't talk about right now, which are focusing aids, which will make it easier. For some cameras, and again, depending on the lens that you've put on the camera, you may be able to use live view focusing if you have that on your camera. Typically, you need to work with a bright star, and if it shows up in your live view, then you can zoom in, usually by a factor of about 10 or so, and you adjust the focus until that star image becomes as tight as possible. And as it gets tighter, you'll notice it gets brighter because you're concentrating its total light output into a smaller and smaller space. When it's as tight as possible and it's as bright as possible, that means you've pinned the focus. Okay, so that's an easy way to do that. If that bright star is not in your area of interest, like I'm going to suggest a homework exercise for you here, a takeaway exercise. For instance, shooting up at Polaris. Polaris is reasonably bright. It may not register on your live view. You may want to swing around to something like Vega temporarily, a nice bright star somewhere in the sky, to do that, to try the live view focusing. If that doesn't work for you, then it's up to your eyeballs, right? You've got to look through your viewfinder, and again, use a bright star, get that focus as tight and bright as possible, and have at it. And then as you take shots, you can have a look at these shots. You can zoom in on them on your preview screen and see if the focus looks really tight. And if you just nick it a little tiny bit, one way or the other, take another shot, compare. you can sort of work your way into the sweet spot of the focus that way if you're having trouble seeing it in the viewfinder. The important thing to remember is that with today's cameras, you would think that you would set the focus to infinity. No, that's not the case. The cameras are designed to accommodate things like infrared imaging and all that type of stuff, where you focus at a different point. So from the perspective of visual or visible light focusing, the camera will actually focus beyond infinity. So your sweet spot is actually somewhere on that focusing ring before the infinity mark. So you have to play with that. Don't just assume. In the old days of film, often it was the case where the lens, if you smacked it over to the infinity mark there, you were good to go. Not the case anymore. Okay, so learn your camera. First thing, do that at home. Don't do that at night. Don't do that when you're out in the field. You want to learn your camera and its capabilities before you get out in the field. Okay, so practice setting up all your equipment, your tripod, all of that stuff, because it's also easy to forget things at home, like power packs and spare batteries and stuff. Make sure that you've got all your kit together. And then find yourself easier said than done, a clear moonless night. We haven't had too much of those in the last 6 months, but they are available from time to time. And plan on spending a couple of hours playing with this. Simple as that. Thank you. So choose a clear moonless night. Dress accordingly, because if you're out at FLO or out in somewhere else in the field, depending on when you're shooting, bugs or cold evenings will really temper your enthusiasm, trust me. So dress accordingly. And then pick a convenient site. So as this is Astrophotography 101, I would suggest your backyard. That's a good starting point because it's close at hand. And it'll also give you a baseline to think about when you start your shooting, because most of you live within city limits. You'll find that it's very different shooting than when you get out to a site like FLO or Lennox Addington, where you've got dark skies. You're going to use a whole different pile of settings. But shooting in your backyard is a good way to become at least familiar with things and your camera operation. So what I'm suggesting is, if you want to give this a try, try aiming your camera at Polaris. You can try to do some star trails around Polaris. Polaris is easy to find. Most people know how to find that star. It's reasonably bright. The nice thing with Polaris is too that if you're using a nice wide-angle lens, like anywhere from 14 millimeter to like 50 millimeters or so, you're not going to get a lot of motion at Polaris, even if you're shooting all night long, because essentially all the stars seem to rotate around Polaris as the night goes on. As you get away from Polaris, you'll start to get star trails, and that's what you're going to try to shoot. It's really, really simple. You're not doing anything too heavy duty. You'll wind up getting something like this. So set up your camera, aim it at Polaris, do your focusing, and then just try a pile of shots. Anything from 5 seconds to 5 minutes, whatever your conditions will allow at your site. Certainly, if for those folks living within city limits, 5 minutes, you're probably going to blow the view. It'll probably be too saturated. If you get out to a site like FLO or Lennox Addington or any site outside the city, you can go for considerably longer doing a shot like this, and you'll get longer and longer trails. Okay, so for your homework assignment, essentially, this is a really, really basic exercise. Set up your equipment once you're on site. Find an aim at Polaris. Set your camera settings. Do the initial exposure at around 10 seconds just to get comfortable with things. When you go to adjust your lens aperture, set it to lowest setting to start with. That means your aperture is fully open. You're going to drink in as much light as possible. Set out initially a high ISO level. Eric mentioned that we start out high and then maybe back it off to the point where the image is still acceptable. And the lower you can go, the less noise will be in your image. But try to start high first, so at least you're seeing that you're getting something. And then remember to set your camera to not record just JPEGs, but the raw images as well. You won't use the RAWs right now. We'll get into that at a later session. But the important thing to remember is that JPEG is really, it's a lossy format. In other words, you're throwing away data that you've paid good money for your camera to collect. And it's compressed, so it's not quite true. You use JPEG as a kind of a final display format. The raw images contain all the data that your camera is capable of collecting. And as you get into processing your images, you'll see why we need that data to make things nice and smooth and to bring out fine details. So just collect them for now. Yeah, it's going to eat up a bit more disk space, but don't worry about it. Yeah, disk space is a lot less expensive these days. Focus your camera, like I said, use live view if it's available. Use a bright star. You can even use a planet if you need to, but remember, with a planet, it won't focus down to a point because they are extended disk objects. But at least you'll see you'll see the image getting tighter and tighter and brighter, and that's really the key point. And again, remember, the focus is not at the infinity setting of the lens. And so, the other thing I recommend is when you get out in the field to do this stuff, take a little notebook with you and jot down what you've tried, because it's, otherwise you're going to have to go back. If you've been shooting for an hour at different settings, you're going to go back and say, what was the first thing I set? What was the second? So you don't want to have to repeat things, right? Keep a log of what you're shooting and give it a check mark if you think, wow, that's a good result, or oh, too bright. And then it's easy to go back and make subsequent adjustments from there. Again, as I said, shoot a series of images at different exposures and different ISOs. Experiment with your camera, and typically start from low, 5-10 seconds, and then bump it up from there and see what your site will allow. As I said, in the city, that's going to be a lot shorter than it will be in the country. That's pretty much it. Yeah, and so again, down at this point, when you've experimented like that, when you've taken a shot, especially if you're aiming at Polaris, shoot a sequence of images. Don't make any other changes, just shoot a sequence of images, and we'll wind up doing maybe a bit of a time lapse like Eric. Or what you can do is, we'll show you this later, is how to put images together so you can get long extended star trails using short images rather than trying to capture an extended trail in one image, because that doesn't really work too well. So essentially, what I've done here, again with taking a sequence of shots, this is the same basic approach that you would use for shooting things like star trails, auroras, as people saw a week ago, meteor showers, and time lapses. Same mindset, and really it boils down to learning your camera, learning what your camera can do. The final thing, when you're out in the field, again, this is for later use, but take a series of dark frames. We'll get into this when we get into the image processing. A dark frame is really just you capping your lens so that no light's getting into the camera that way, and then shoot about a dozen or so images at the same settings that you found was your sweet spot for when you were doing actual imaging. The dark frames we'll use later on to do some noise reduction in the imaging, but we won't get into further than that. So give it a try if you're interested. And again, if you want some of these slides here, I know some folks taking pictures of them. Like I said, send me an email and I'll send you JPEGs of these slides so that you have your list in front of you. And good shooting, good luck, and let me know how you do. Thanks a lot.
Well, can I see the lights up a little bit, please? I'd like to see the audience when I'm speaking to them. And I want to see my notes also. Well, good evening, everyone. Thank you for all coming out on a great night. Hopefully, you bought a lot of good things at the swap table. So, one fast slide before we start is the aurora from last weekend. Oh, yeah, it's true. I got the clicker. Oh, I'll screw this up. Not bad. Who saw the aurora last weekend? Round of applause. Can't see. Excellent. Good. Who took pictures? No pictures? I was up till 4 in the morning shooting. This is one of the best ones. Took about 30 good ones. The aurora kind of went up and down. We had striations, so I like this one. So, well, many of us have had a passion or have a passion for the night sky, and my story begins at the age of 8. Ever since the fateful day in September of 1965, yes, I was born in 1957, 1965, pulled a book out of the elementary school library entitled Stars. And right there the book glowed, and I knew this was it. Well, my good friend Joe Bonner, who's sitting here tonight, actually gave me a copy of this book for my birthday a few years ago. It was a paper copy. And just the memories kept on flooding back. And one thing that really struck me was just the size of the Earth compared to the Sun. It's like a pimple on the face of the Sun. 109 Earths fit across, over 1 million feet inside, 93 million miles back in the old days. Colors and stars, dimensions, just fish out of water, never stopped for 52 years. Well, I joined, in fact, I worked with a colleague back in 1976, whose husband was with the Montreal Center of the RASC years before, and apprised me of the RASC in Montreal. Of course, I joined right away. Well, this picture was taken in 1955, taken from the RASC website. But here we have Isabel K. Williamson, and in fact, we have Constantine Papakosmos and Bill Stropel here in the audience, came down from Montreal. Great to see you guys again. And this was our clubhouse for years upon years on McGill University property, just behind McGill Stadium, the football stadium right behind it. We had a CA telescope, fantastic. And our meetings here, Saturday nights was for public, Wednesday were just for members. So a lot of great times for sure. So here we are into the darkness, my first taste of being out in the great outdoors. And in Montreal too, that's where I first met David Levy. He was just a young guy working at a campground for kids, showing the moon, whatnot. Well, in Montreal is where I also met Alistair Ling. And for years upon years, we traveled from Montreal to Vankleek, which is called Cedar Crest Observatory. It was pretty well property of one of our late friends, Fred Clark. An hour and a half away in a Volkswagen Rabbit with no suspension. 4 months of the year, of all 4 seasons of the year, has some great skies. In fact, my first time out there, I couldn't even find the Big Dipper. They all looked the same, but then I got the hang of it. Here in Ottawa is where pretty well outreach came to my passion. For 15 years, I was teaching at Algonquin College, just a beginner's course from 1995 to 2010. Also taught at the skimming, Bill Mason. Also had many star nights with the old slides and my telescopes at KOA campsites. Even my granddaughter Abby, who's 7 years old tomorrow, loves to look at Jupiter. So I did a lot of kids too. And now going to a lot of senior residences. Obviously, we don't go outside, but just do PowerPoint presentations inside. And the questions that they ask, the 80, 90 years old, what they ask is phenomenal. Their brains are still sharp. I was introduced first to astronomy or to radio back in Montreal. In fact, it was one of the DJs from CJAD, Mike Kramer, actually came to the Montreal Center just to see what we were doing because I had mentioned that we were having a meeting. Well, he invited my cousin and myself to the radio station that night because he was the 11 p.m. till morning show. So the studio pretty good. He actually put me on air that night to speak about astronomy, the RASC, and the Montreal Center. And from there I was hooked. I figured this is the best way to get the message out to everybody in radio land. Because people listened in radio cars, well, back then, not even Sony Walkmans. But here in Ottawa, then the outreach really began on radio. I was very fortunate with Lowell Green to be in the studio, who he never had pretty well guests. I was on 4 times in the studio. Then Steve Madeley in the old days. Now with Brian Lilly and, of course, Edmund Solomon. Also television on the bottom. That was the next line of bringing out to the people. Here with Leanne Cusack, I was on 11 times at the old CJH studio. I called my usual 23 minutes. It was right after the lunchtime news, show images of the nighttime sky, what's coming up, and also field phone calls, which was pretty interesting, live on the air. But my ultimate was with the naming of the asteroid after me, and to be on CTV News Channel, which was nationwide live, and to have only a 4-hour getting ready scenario. I was offered at lunch hour, and I was supposed to be there at 4:40. For a time too, I had my observatory in Barrhaven, which I must rebuild in country, still crowdfunding for that. It did. But I had my beautiful observatory. I was even able to webcast from my observatory over the internet. And this is pretty well an astronomy 101 on what people are looking at, planets or the moon or distant galaxies, and again, just outreach to the hilt. And we're taking outreach further. Later on this month, I've been invited to be guest speaker for a private convention at the K-Rock Center in Kingston, in front of as many as 1,500 people. So say a prayer for me that day. But it comes down to outreach, which a lot of members here do outreach. We have great star parties at CARP. We have solar observing, which was last weekend. So we have many dedicated members here in the Ottawa Centre, across the country, and around the world that do this very, very well. And they should have a round of applause for what they do. And easily at some of these start parties at CARP, you can have 30 telescopes and up to about 300 people that attend. So it's just crazy, but in a good way. So, back in February of 2016, about a year and a half ago, a year and a bit ago, Peter Jedicke approached me, and he was actually getting a list ready of prospective names for asteroids. And knowing what I've done with the RASC for over the decades, such as when I was in Montreal, I was librarian, director of the observatory, director of observational activities. Of course, here in Ottawa, city on council, national council rep, chair of light pollution abatement, vice president, meeting chair, and ultimately president, and now past president. So with the dedication with the RASC, oh yeah, also in Montreal too, I ran the Sky News, which was the magazine, or the newsletter of the old Gestetner, the inky Gestetner. What a mess that was, what a mess it is. But it was fun times, it was fun times. So everything with, my name went in, hoping for the best, and on April 14th of this year, my wife Debbie's birthday, of all things, I get an email from Peter, headline asteroid. Well, nervously, I read the email. It went on to congratulate me that the IAU, International Astronomical Union, has officially named 22406 Gary Boyle. I'm now in the books. The IAU actually hands out recognition for past accomplishments. It's not just astronomers, amateur or professional. It could be anywhere from teachers, yes, even politicians, a couple US presidents, biologists, chemists. The field range is enormous, pretty well everything. Music, even Freddie Mercury has an asteroid named after him. Mozart has one named after him. So I'm in very good company. And of all things, thanks to Eric for sending me the screenshot from Sky Safari, my asteroid, which is from Sky Safari, the database has not been updated yet. I don't know how often they do it, maybe once a year. But here's my asteroid on June 22nd in the Pleiades cluster. This is not doctored, it is really the Pleiades cluster. So Eric has graciously offered to try to image this. It's about 20th magnitude, but should break to about 19th by the time it comes around. Yeah. It's about 3 kilometers wide, orbits the sun, one lap every 3.5 years, and close approach is 327 million kilometers, so it's probably about 500 million kilometers now, so very far away. But to have it here in this field of view is just incredible. So just in closing, I'd like to thank my wife Debbie, especially my wife Debbie, for allowing me to do what I've done for decades. We've been married since 1982. In October this year, it'll be 35 years of marriage. Wow. And to have an understanding spouse, no matter if male or female, to allow you to go out to that hour and a half away and come back at 4 o'clock in the morning and not get a skillet in the head. That's pretty good. And also when I had the observatory in the backyard again, being out all night long. So many hours I've been away from her presence, but she knew that I was doing what I love to do. And that's really to share with everybody. So with that, I shared this award with her too. So, and as I said, to be in this fine company of great people and great historians and important people in the past and present, I am both humbled and honored. Thank you.
Good stuff, Gary. Okay, so now we're going to go to the observation reports. If we could get all the guys up on the screen down here, and we'll proceed right with that.
All right, we're trying something new. I've got my notes on my phone, so I can read it in the dark. So, everybody recognizes the moon? No. Good, good. We learned that Venus is coming into greatest western elongation later in the month. Back at the end of March, it was actually in conjunction. This is the time when Venus and the Sun are basically in a straight line from the Earth. So in this case, Venus was between us and the Sun. Now normally when we think of a planet as being in conjunction, it means it's very close to the Sun. It rises and sets at the same time as the Sun. You're not going to see it. And so generally we lose the planet for a few weeks or a month either side of conjunction. In this case, Venus is very bright, and it was also going by 8 1/3 degrees north of the Sun. So this follows on from something I've been trying to see if I can see the new moon when it goes by north of the Sun. I haven't succeeded that. But I thought, I wonder if I can see Venus during daylight when it's straight north of the Sun. Now, unfortunately, of course, as we came up closer and closer to the date, the forecast was not looking good for Saturday, March the 25th. So on the 22nd, I had been observing out the evening of the 21st all night. And so in the morning, I just left my telescope set up, left it focused, left it aligned to the sky, so that hopefully I could slew to Venus. Now what I actually did in order to save my eyes and my telescope and my camera was I put the solar filter on the camera, I slewed to the Sun, adjusted it till the Sun was nicely centered, and then told it slew over to Venus. Look through the eyepiece, there's no sign of the Sun in the eyepiece with the solar filter, so now I know it's safe to take the solar filter off. And I must admit, it was a lovely view. Little Cheshire smile in the sky, very thin. Unfortunately, this actually is an image. This is a video taken with my Canon 60DA in its high resolution mode, 9 centimeter f4.5 Apple refractor. The turbulence was absolutely appalling. So I don't know. If you look very carefully, you can see over here on this side, there's a couple of filaments that give you a hint as to just how really narrow the actual crescent was. It was probably somewhere about, certainly no more than a quarter as wide as what is showing here. I also tried imaging in the red, hoping that it would increase the contrast and maybe reduce the turbulence a bit. I also tried the 40 centimeter Boltwood scope, imaging it at 4 meter focal length, and essentially I got exactly the same thing, just a lot bigger. So, essentially, that's the best I could do. However, I did see it, and it is a lovely thing, and the next time it happens, you should all go up and look. Comet 41P Tuttle-Jacobini-Crescent has been traveling around over the past few months. This is shot with my 9 centimeter refractor and the Canon 60DA, a couple of hours of exposure. I don't know if it shows up here, but if you look carefully, there's a kind of a ghostly striation all over the image, and I haven't figured out what's going on, but these are stacked in Deep Sky Stacker, and it actually has a comet stacking mode where what it does is it aligns all the images on the stars and adds them all together. Then it aligns all the images on the comet and stacks those all together. It figures out what the comet looks like, what it would look like as it trails across, then it subtracts that trailed image from the stars, and then it adds the two images back together, and you end up with an image which is stacked for both. And, but it does show up the nice green color. You can sort of see a hint of a tail extending off in that direction. This is the same comet done with the 40 centimeter, just monochrome. This is just 5 or 10 minutes of exposure, a lot larger size. One of the things I was hoping to do with this, there is an international program where you can send the images off, and they're going to try and make use of the morphology of the coma and its changes over time. Comet 45P Honda Merkos Pajdusakova. This one, oops, all right. You can see the nucleus there. These are done with a CCD camera on the 40 centimeter, and so I'm just stacking them on the nucleus of the comet, so the stars all end up trailed. This one you can actually see has the anti-tail, it's called, so the main tail goes up here, and what's called the anti-tail comes down here. And if you want to figure out how those work, if you sort of think of the comet as having a dust tail and a gas tail, and normally we see it up in the sky with the dust tail sweeping off in an arc and then the gas tail coming off. But in certain orientations, the comet, we're actually looking at it this way. And so what you're seeing is the nucleus of the comet in the middle, the dust tail coming out one side, and then the gas tail, or even possibly parts of the dust tail, coming out the other side. So we're actually looking right at the end of the comet as it's presumably going away from us. I tried imaging this a few weeks later, and it was almost gone. It was very difficult. Comet Johnson, this was mentioned earlier on as well. So here you can actually see, here's the dust tail extending out this way, and then if I way over process it to the point where it's really ugly, you can actually see there's a hint of a gas tail out there. The reason the dust tail comes out in a curve is because the particles of dust, after they've left the comet, they actually start to orbit the sun in their own orbits. And so because they've been pushed away from the sun, well, I guess I keep doing that. Because they've actually been pushed away from the sun, they go into a slightly slower orbit, and so they tend to trail behind, whereas the gas tail is just ions, and so they just stream away in a straight line. So, Horsehead Nebula, this is an H-alpha and RGB image, so it's actually done as two separate images in H-alpha for a total of about, well, it seems 6, 12, 20-minute exposures. And then with the same telescope, I took a full frame with my Canon DSLR and added it on top. It's quite a fussy process adding the H-alpha to the RGB images, but it works fairly nicely. So you can see the Horsehead in here, and then the Flame Nebula over here, and this is one of the stars of the belt, which extends over there. This is an interesting star here, if you ever read about them, the Sigma Orionis, which is actually a sextuple star. There's 6 of them flying around together. M81 and M82, well, we've seen lots of pictures of that. Probably bigger pictures of them. But what this is actually a picture of, this is called an integrated flux nebula. And if you look down here, you can see a faint glow in the sky. This is only about an hour-and-a-half exposure from my place, about 2/3 of the way to Kingston. So it's not terribly dark skies. And I didn't think this kind of thing would be detectable from up here. Normally you see it taken by guys in Australia or New Mexico and stuff. So it is there, and I'm going to be trying some deeper exposures. Essentially what this is clouds of gas or dust that have been blown up generally above the disk of the galaxy, and it's actually the integrated starlight from the galaxy that's illuminating them. So then I had to do a closer up version of M81 and M82 and some of their companions. M95 and M96 and M105 and one of its companions in the front end of Leo, and Markarian's chain. This is M84 and M86 here, and then Markarian's chain extends up here. This is if you've got a largish scope, my 12.5 inch or even better Rob Dick's 24 inch, you sweep up here, you can pull up 100 galaxies in 2 or 3 minutes. And then we've got another couple of the big M objects down here. And M98, 99, and 100. Some nice, I was quite surprised. This is only a 400 millimeter focal length telescope. And so it's, you know, but you're still getting a lot of, some nice spirals in here, which is nice because a lot of the ellipticals tend to be kind of boring, just big fuzzy blobs. So, thank you.
Thanks, Rick. Those are pretty good images there. Next up, we have Bob Olson, and he's going to make your day.
Yeah, I'm going to make your day alright because I don't have my notes on my phone. I have no idea what they say. When I image, I tend to look at my observatory. I look at my planetarium program, which happens to be Starry Night, and I just see what there is to see. And you can see that right in the middle of the field where I wanted to look at was this thing called make. I have no idea what it is.
Maki.
Yeah. So anyway, so I looked it up, and it was the biggest print on the whole screen, and it's pronounced Maki, and it's actually a minor planet. It's the second brightest minor planet after Pluto, and it's a little further away than Pluto too. It has a moon which is about 160 kilometers in diameter. I think that Maki is actually about 1,400 kilometers in diameter. It takes 310 years to orbit the Earth. Orbit the Sun, and Pluto takes about 15 or 20 years less than that. So it's actually further away than Pluto. Now that'd be fun to image it. I can remember Brian McCullough talking about finding Pluto. So I took a picture of it. And you can see that this is, roughly the same thing that it was in my field of view on the planetarium. And if you put some labels on it, you can see Maki there. Except you really can't. So clearly you've got to get in a little closer. And this is just a crop of the same image. So I cropped it down to that, and then we'll get a little tighter. And it's still a little difficult to pick it out. So we'll switch it to, I could read my notes now. We'll switch to a negative image, which makes it easier to see objects. And there it is right there, taken on May 15th. And you say to yourself, how do I know he just didn't randomly point an arrow at a dot? Like, who the hell here would know? And so the trick is, take a picture a few days later. So here's the 19th. So there you go. See it hop across? And I actually cut, that's the right distance it's supposed to move. So, so there you go. It's named after a Easter Island god of creation. All right, next image. North American Nebula. I sent this picture in after I took it, and Richard Harding, a friend of mine, said, Bob, I really like your images because I'm getting sick and tired of the North American Nebula and the
Pelican.
No, the big flowery one.
Oh, the rosette.
The rosette, yeah. So so I sent it in anyway. Now this picture here is monstrous field of view. I mean, just to give you some idea, it's 3 degrees by 2. The full moon would be that big. My normal imaging camera takes the picture just of the full moon. So you can see, I mean, I have to take 30 pictures to get this in the field of view normally. And this is a hydrogen alpha RGB image. Thank you.
All right, so next up we've got Taras here. We're going to squeeze him in for at least a couple of shots.
I will only need 25 minutes, that's fine. So, yeah, I have only 2 pictures. This is thanks to Bob Olson, who told me last time when I showed this picture that I should look more carefully. This is a picture of M63 galaxy and supernova explosion in it. When I took this picture, I did not pay attention, and I could not believe actually that the supernova will show up, but it did. Oops, it's this little thing here. After pushing the limits in the processing, as you see, there is lots of noise showing up, but I managed to capture apparently that supernova explosion a few days after it happened. It was roughly magnitude 18, 19, so it's not too bright, but it's there. And this is actually not a regular, it's a little bit kind of rare. If I'm not mistaken, it's type 1A supernova, and there is 2 stars, a double star. One is regular and the other is white dwarf when they're orbiting each other. So at some point white dwarf accretes the matter from a neighboring star, and when it reaches the critical mass, it explodes, and that's what happened. And this is second attempt of taking another supernova shot from in another galaxy. Well, actually, I should correct myself. This was not in a galaxy M63, but 40 times further from us. It's behind that galaxy. So it's about 1 billion light years away. So it's quite amazing that even though that event is really bright, incredibly bright, but 1 billion light years away, the light still reached us, and we can still observe it here on the Earth. While this is explosion of supernova in Fireworks galaxy, and the name of that galaxy, Fireworks, is apparently due to the fact that it's one of the most intense star-burning regions among the other galaxies that are known to us. There is an average 1 supernova explosion every 10 years happening. So last century there were 10 reports of supernova within 100 years, which roughly matches the pattern and thus the name Fireworks galaxy. And a few days ago there was actually one more explosion, which is this one. Oops. So it's pretty bright, it's still there, and it took me the second attempt to improve the picture a little bit. The first one was in a very, very brief period of time when the skies cleared out, when we went with Eric to some distant place, and with not much hope of seeing anything, but there was an opportunity to capture 5-minute exposure, but the pictures didn't turn out well. So last weekend, when there was an event at FLO Observatory, I took this picture, and I'm happy that the supernova is still there, and you can see it here again. Very rare event, but very luminous. Thank you.
Okay, next up, I think Robert is going to show his son's image of these wonderful auroras here.
Last time Jonathan was here was 14 years ago. He's now 20 years old. So unfortunately, he's a videographer, and he's working on a contract with 3 music videos. He's the videographer and the creative editor. So he's busy tonight, and this is, you'll of course remember last weekend there's an aurora erupted, and during the open house at my observatory, I gave him a call, suggested he go down to the Ottawa River. So this is a picture he took from Westboro Beach, and it's taken with his A7S Sony camera and f2.8. It's a 24mm telephoto lens. at ISO 6400. And pretty good composition. Of course, you can see the problem with outdoor lighting for security lighting. He couldn't show much of the good stuff over by the pavilion. Anyway, that's all I wish to show for now. Thank you.
All right. Sorry for this taking so long, guys, but we're now here at the feature presentation. Jim, if you could come up and let's learn how to observe the sun. Get a little bit more light on the podium, please, Chris.
So, some of you may recognize the slides from tonight. If you came to the workshop that was a couple of months ago on the sun. So if you have seen this before, just maybe have a nap or go to the washroom. But what I'm going to talk about fairly briefly tonight is all the different ways that you can observe the sun, and when you're observing the sun, what it is you can look for. And this is kind of to get you in the mood for this August when we have the solar eclipse. So the first thing that's very important to get across is that you have to be safe. There's a lot of energy coming from the sun, and if you're not using the correct equipment and using it carefully, you can injure yourself very badly. Just the visible light alone is enough to damage your sensors in your eye. Plus, if you add on to that the fact that about half of the sun's energy that we receive at the surface is in the infrared band that we cannot even see, it is there as well. You're basically blinding yourself as well as cooking your eyes without using the correct equipment. So, be safe, please. So very quickly, we'll have a look at what the sun is actually, how it's kind of put together. The sun's a fairly typical star of this mass. There's a central region, the internal region, that consists of a core. It's about the middle 1/4 of the radius. That's where all the energy is produced. Outside of that is a layer called the radiative zone, and that's where the energy from the core is working its way out to the outside through primarily radiation as the heat conduction method. And then there's the outer 1/4 called the convective layer, where the heat is conducted through actual motion of material carrying the heat out to the outside. And then outside of that layer, there is a very thin area that is what we actually, as amateurs, are able to observe. There's the photosphere, which is what we see with our naked eye. It's the point where the gases have cooled enough for photons to suddenly be unhindered by the plasma, and they're able to travel freely into space, unhindered. And that's what we see. That's called the photosphere. And above that are other layers of gas of different temperature. The immediate layer above is the chromosphere, and then above that, a much larger but more tenuous layer called the corona. And I'll talk a bit more about that later on. Now, just a little piece of trivia. A photon generated through fusion reaction in the middle takes anywhere from 1,000 to 1,000,000 years to work its way all the way out from the middle of the sun to the photosphere and off into space. So fusion could stop, photons stop being created, and we wouldn't know within our lifetime, basically. So how hot is the sun? Well, you may have noted on the earlier slide showing the black body emission of the sun that it's equated to a black body temperature of around 55 to 6,000 Kelvin. That's just the perceived temperature at the photosphere, what we see. If we look starting in the interior, the temperature actually starts around 10 million degrees Kelvin. And that's a combination of the pressure, the energy released from fusion, as well as all the gravitational potential energy from when it was originally created, caused this high temperature in the middle, and that's what's sustaining the fusion. And as you travel, As you travel out from the center, the temperature gradually goes down. Not very quickly through the radiative zone, because the radiation is not a very effective method of transferring the heat, but as soon as you get into the convective layer, the temperature drops very quickly until you get out to the photosphere where it's around 55 to 6,000 degrees Kelvin. Now, if we look outside of the photosphere, some funny things start to happen. The temperature goes down like you would expect, but then it goes back up again. And there is an explanation for this. We don't have enough time to go into it tonight, but if you want to ask me later, I'll give you a lesson in Alphen wave turbulence heating. Anyway, so the photosphere is kind of in that 6,000 Kelvin range. The chromosphere is also a similar temperature. And then as we enter into the corona, that's when the temperature climbs back up into the 1 to 2 million degrees Kelvin range. Now, these symbols here in the colored text, they indicate elements with a particular emission line that is observable in that part of the sun's atmosphere, because at that particular temperature, that's when that emission line is really strong. So for example, in the chromosphere, hydrogen alpha, which is around 656 nanometers, is a very strong emission line. Similarly, up in the corona, these higher ionizations of iron have very strong emission lines when they're up in the 1 million to 2 million degree temperature range. And this actually gives us a way of observing each of these layers. If you observe in the particular wavelength of that emission line, then you can actually observe one layer as opposed to another layer. And that's actually something that we as amateurs are able to do. So if you want to observe the interior as an amateur, yeah, forget it. Unless you want to build a neutrino collector in your basement, I don't think your wives would be too keen on that. Well, maybe they would, I don't know. You pretty much have to leave that to the scientists with helioseismology and the massive neutrino sensors. Just find out what's going on the interior. But on the exterior, you can very easily observe the photosphere with visible light. And I'm going to talk more about that shortly. The chromosphere, you can use a wavelength of calcium 2K. That's a very specific wavelength emitted by calcium, and it's just in the near ultraviolet range. And if you want to observe the upper range of the chromosphere, you can use hydrogen alpha, which a lot of you may be familiar with. And if you want to observe all the way up into the chromosphere, unfortunately, those wavelengths of iron emission are deep, deep into the UV, and you can't actually observe them beneath the Earth's atmosphere. They get absorbed. You have to observe them from space. So our only chance of observing the corona is with white light, but during an eclipse, when the sun's emission has been removed. I'll talk a bit about that more later. So white light observing, the idea is to lower the intensity of the light coming in to a point where it's safe. There's a number of ways you can do this. All of them you can do using the scopes and binoculars or whatever you have currently. You don't have to go out and buy something special. And it is the most economical way to observe the sun. The easiest way is to do something called rear projection. Let's take your existing telescope with an eyepiece and instead of putting your eye up to it, you use a piece of paper or cardboard to project the image onto it. Then you look at the projected image. You can see sunspots for sure, but you're not probably going to see any more detail than that. An even simpler way of doing this, if you don't even have a telescope, is to make a pinhole camera. And that's a fun experiment to do with kids at home, actually. And there's lots of places online you can find instructions how to build pinhole cameras. The next level up in cost, but also in the quality of the image, is the use of solar filter. And these are made either of glass or of a thin mylar, and they have a special coating that removes almost all of the light to make it a safe level to observe. And they go on the end of your telescope. They come in any size. I have examples here that you can see after if you want. They're reasonably affordable. They range in price from $20 up to $100, $150. And like I said, for any size of scope. You can see nice sunspot detail and granularity and some other details like filaments along the sides of the edges of the sun, and you'll see some pictures later. The most expensive solution is something called a Herschel safety wedge. It's an idea that John Herschel came up with, and then it was later fine-tuned by Ignacio Porro back in the 1800s. The idea is that you use a prism that's wedge-shaped to direct most of the sun's light out the back of the prism. You can see here, this particular device, most of it's coming out the back into the ceramic disc where it's harmlessly dissipated as heat. And then the small percentage that's left gets directed up to the eyepiece. And this produces the best quality images in white light, but it's also the most expensive solution. It sells for around $700 US. These are a couple of sample images that I collected. All the images tonight of the sun are collected by me from my backyard in the Alta Vista area to give you an idea of what's kind of achievable, even as an amateur who's been in it for only a couple of years. So the images on the right are with a Herschel safety wedge. Images on the left are with a Bader solar film, the reasonably inexpensive material, to give you an idea of kind of what you can see and what's achievable with this type of equipment. The two color images on the bottom are from me adding additional filter in an attempt to further enhance the contrast. So, what do you look for when you're looking at the sun in white light? Well, the most obvious thing is sunspots. You can see sunspots to pretty much any of the methods, any of the filtering techniques that I just mentioned in the slide previously. Now, there are some details that you can look for when you're observing the sunspots. For example, there are different types of sunspots. There's unipolar sunspots, where it's a single spot sort of by itself, or a bipolar sunspot, where it looks like they're traveling as a pair. And in fact, they have a different magnetic polarity. Within the sunspot itself, there's some details you can look for. There's the darker center called the umbra, and then a slightly lighter outer ring called the penumbra. It's just like with an eclipse, dark shadow, the lighter shadow. And if you have really good seeing, you might actually see what look like little flames or petals of a flower in the penumbra. And those are called filaments. And around the sunspots, you'll see kind of a texture that are called granules. And sometimes you'll see granules that are a little darker than other granules, and they're called dark granules. Not very original. And you might see some of those dark granules that, if you watch them for an hour or day to day, they'll get bigger. And those are called pores, and those will either disappear after a while or they will eventually grow into new sunspots. So those are the kind of things, if you see them, to keep your eye on to see how they change with time. Another thing that tends to change with time, even in the course of 10 minutes, is something called a light bridge. So across the umbra, sometimes you'll see a line that divides it up into 2 or more pieces. And in some cases, it can totally slice the umbra up into chunks, in which case it's called a streamer. See how it's kind of a zigzag pattern here that's cut up the umbra. And that's something, even when we had the solar observing there last weekend, this was actually happening to the small sunspot group that we had that day. Now, in white light, mostly on the limb where it starts to get a little bit darker, you can see something called faculae. And this is, from what scientists understand, is an area of slightly decreased magnetic activity which causes a slight brightening. It tends to happen near sunspots, but it's really difficult to see it on the disk in the middle. You can really only see it well on the edge. And granules, that's this overall texture. You know you have good seeing and that you have your equipment nicely focused if you can actually see these granules, because they are quite small. They're, I believe, I can't remember if I wrote it down, they're on the order of several thousand kilometers across. Fairly small in the grand scheme of things, but if your system is working well and the seeing is cooperating with you, you can make them out. And they're actually individual cells of convection, small scale convection. So we have hot gas rising in the middle, so it's bright, and then it cools and falls down around the outside, so it's dark because it's cooler. So you have all these, whole array of these convection cells. And as I mentioned, the limb darkening, it makes it appear like it's darker on the edges, which helps you with seeing things like the faculae. It's a radiative effect. If, the way a ball emits radiation into space causes this optical effect. It's not actually a lower temperature, it's just an effect of the angle of the surface to the observer. Now there is also something called a flare. Now people often get flares and prominences intermingle, but a flare is a very specific term. It refers to a very sudden, intense release of magnetic energy, and much easier to see in a calcium K and H-alpha, but you can see them in white light if you're lucky. And it's an intense enough release of energy, you can see it, and it'll be a unusually bright patch, usually around a particularly active group of sunspots. So that's another thing to kind of keep your eye open for. So moving along to calcium K. So now we're looking at a very narrow band down in the near ultraviolet, around 393 to 398 nanometers, just outside of our visual range. Different filters have different widths. They can go from a half an angstrom up to 80 angstroms in width, depending on how much money you want to spend. You use this with an existing scope, plus you have to add on an energy rejection filter, something that cuts the intensity of the light coming in before it gets to the filter. And this is quite a bit more expensive way to observe the sun compared to white light, and you can only do it with a camera. You can't actually see this wavelength of light. Some people kind of can, but you're not going to get nearly the detail that you would if you use it with a camera. So that's kind of an added expense. There are again kind of three levels of calcium K observing. The method that I use is a screw-on filter. So this is a fairly narrow bandpass filter. You add it to your existing system. I use it with my Beta Herschel wedge. There's a number of different suppliers out there that sell these. You can have a fixed etalon. So an etalon is sort of a fancy, high-precision type of filter. And they tend to be tuned to match very carefully the bandpass that you want. The less expensive ones you buy are fixed at the factory. You can't make any adjustments. And there are a number of them out there. There's currently you can still buy this this one from Lunt Systems. Coronado used to make a PST version that was calcium K, but they don't sell it anymore. You might find it used. But these give much better quality image than the screw-on filter, but they're also quite a bit more expensive. And then top of the line would be an adjustable etalon, either a tilt-tuned or temperature-controlled. And these are the most expensive, but they produce the most amazing images. It might be hard to see the prices on the bottom, but this filter that I bought cost about $200. These cost in the range of $800 to $2,000, and these cost $1,200 to $6,000, depending on the quality that you get. So these are the types of views you get in calcium K. Similar to white light, but there's a lot of new detail that is added to the image because we're now looking at a layer that's slightly above the photosphere. So there's a lot of similar features here that we would have seen in white light. We have, obviously sunspots with all the same features. We have pores, we have granules, we have bipolar, we have unipolar sunspots. We get dark granules and we get limb darkening. This is all stuff we can see in white light. But there's some unique things, like these lonely bright specks that kind of drift around, not associated with a sunspot group. They're called K-grains. You also get these bright areas around sunspot groups, but also out and away from sunspot groups, and they're called the plage. It may look like they're the same thing as the faculae in the white light, but actually they're not directly related. Scientists don't understand what the interrelationship is, but they are different phenomena. Plage here is due to an increase in magnetic activity, where a faculae is a reduction in magnetic activity. So there's still some science to do there to figure that out. Now, if you're really lucky and you're getting really good seeing, I say that a lot, you might be able to make out a larger scale pattern on the surface in the granularity. And it can start around the plages, around sunspots, but it can extend over the entire surface, this kind of a polygonal pattern with bright rings kind of outlining it. And this is called the chromospheric network. It's actually another scale of convection in the chromosphere. So the granularity is small scale, the chromospheric network, and each individual cell is called a super or mega granule. And they're on the order of, I have it written down here, around 30,000 kilometers across each of these cells. So this is a larger scale convection, much deeper, and within that, in the upper range, you get the smaller scale granules. So this is something that you can only see clearly in calcium K. You can see it a little bit in H-alpha, but much more clearly in calcium K. Before we leave calcium K, a quick note. Calcium K emission and H-alpha actually overlap quite a bit. So this is a plot of height from the photosphere and what type of filter you can observe with it. So H-alpha covers kind of a mid to upper range when you look at right on the core band. If you're on the wings of the band, you see closer down to the photosphere. Calcium K, similarly, depending on which sub-wavelength you're looking at, you can see different heights. Almost all the calcium K filters you buy commercially are type K1 or K2, or a combination. So they're kind of restricted to this lower area here. But one interesting thing is, since calcium K overlaps H-alpha, it gives you an opportunity to see something else. This allows you to see prominences, something that people typically think you can only see in H-alpha. But if the prominence is bright enough, and I've been successful from my backyard seeing them, you can see prominences in calcium K. So moving on to the most expensive way of all, hydrogen alpha. So now we're talking a very, very narrow band, 0.3 to 0.7 angstroms wide bandpass filter, a very specific wavelength, 656.28 nanometers. All the options that exist require a tunable etalon. You have to be able to finely adjust to account for what side of the sun you're looking at, whether you're trying to emphasize surface detail or prominences. So the tuning is necessary. And it is the most expensive way to observe the sun as an amateur. But it's also the most interesting. So the least expensive way to go, and that's what I'm using, is to buy an Etalon and blocking filter separately and use them with your existing telescope. I bought a 50mm system, and you can buy adapters to use it with whatever size refractor you have. I get, I think, a very good detail with it. It gives me a lot of options with looking at the surface or prominences. You'll see some of my images later. Next step up is to just buy a dedicated scope, which is essentially taking Etalon and blocking filter and permanently mounting it into a refractor. It allows for some fine-tuning in the factory. You might get a little bit better performance, but that's a little bit subjective. And then top of the line, oh, I have a little note here. Oh yes, there is actually a way of making your own tunable Etalon scope using a refractor and going out and buying Etalon parts and making tuners and things. I tried that before I bought this, and was not very, I wasn't successful, we'll say, we'll leave it at that. It's fun to tinker, but at the end of the day, if you want performance, you kind of need to go out and buy a commercial product. So the top of the line is a temperature-tuned Etalon, and as you can imagine, they are the most expensive. You can pay up into the $16,000 US range to get the top of the line of these. Now, Daystar, which is one of the major suppliers of these high-performance devices, they have a new system out here. That's what's imaged here. That is a lot more affordable. It's kind of in the $1,000, $1,200 range, and they perform very well, but they're not as flexible as their full-blown temperature-controlled Etalons. So anyway, that's kind of what's out there. I brought my my tilt-tuned unit here. If you want to see it later, I can show you. All right, so here are a few examples of the images that I've been able to collect. These are all taken with the same Etalon and blocking filter, but with various telescopes, Barlow, no Barlow, that sort of thing. They're in different colors just because I've been kind of playing around with the processing. Two bottom ones were taken using a one-shot color camera, so the colors were actually red, like the filter gives you. The other two were taken with a monochrome camera, and I was playing with color processing after the fact. So, what to look for when you're observing hydrogen alpha? Well, I'm going to start with the smallest feature and kind of work my way up. And the smallest feature, well, sorry, I'll back up a step. Sunspots and plages, which seem to go together in calcium K, also go together in hydrogen alpha. They tend to be associated with an area of higher magnetic activity in the chromosphere. So that is a common feature to see when there is sunspot activity. There's not a lot right now, but when there is, you tend to see plages and sunspots together. And you can see the umbra, penumbra, and all the other details of sunspot, like in the other two observing bands in H alpha as well. It's what's going on around the sunspots that's new. So the smallest feature to look for is something called a spicule. And it's a very small jet of gas that's being cast off at the surface, traveling at, have it up there, around 50,000 kilometers per hour, give or take, and they're very short-lived, on the order of 10 minutes. So if you watch carefully, and it's easier if you do it with imaging, you can see these features changing quite rapidly with time. So a bush-type spicule just looks like a very symmetrical kind of point of light coming up. And you can actually see them along the limb as well. If they get close to a magnetic disturbance, they might get stretched a little bit and have a bit of a swirl to them, and sometimes they even look kind of like a flower. And in that case, it's called a chain-type spicule. And as I mentioned, you can see spicules on the limb. Okay. Oh, yeah. flip through this a little bit quicker. In the extreme case, when you're close to a sunspot, the spicules get really stretched out into something called a fibril. And they can have pretty dramatic swirling patterns around sunspots. Now, the feature that most people look for is a prominence, which is gas that's being thrown off of the surface, either to go escape into space or to be pulled back down to the sun's surface. And when you see a prominence from above, it's something called a filament. So here's some examples of quiet region filaments. So filaments in areas where there's no sunspot activity. So this is actually this, but looking at it from above. Then there's also filaments in active regions, called active region filaments. And they're actually quite interesting to watch over time. Now, you might see a slightly brightening region off by itself. This is called an emerging flux region. It's an area where the magnetic activity is starting to increase, and that's an area to watch for increase in plage growth, generation of sunspots, and possibly even a flare. So that's interesting to keep your eye out for when you're observing. And it can change fairly rapidly with time. And in this image, I just happened to have caught a flare. This image is reversed, so dark is actually bright in reality. It'll be a very bright area. You'll notice it because if your image exposure is set nicely so everything is nicely exposed, you'll suddenly have something that's overexposed that wasn't there 10 minutes ago, and that is a flare. It's a release of magnetic energy. It's fairly short term. So sorry, I'm speeding it up now. The last level, the outer level, the corona, it's about 1/millionth the brightness of the photosphere, which makes it pretty much impossible to observe when you can see the photosphere. I tried during the day, and because of the scattering in the atmosphere, it is also brighter than the corona, you can't see it. So the only opportunity to do it is during an eclipse, a total eclipse, not even a partial. It has to be a total eclipse. But when that happens, you don't need any filters, you don't need a telescope. You can just use your eyes, or a pair of binoculars, whatever you have. So if you're fortunate enough to have an eclipse nearby, then this is a great opportunity to observe the corona. And it just happens that in a couple of months, there is going to be an eclipse, a total eclipse. Probably the most hyped eclipse in all of our lifetimes. So it's about 2 days' drive to get to the path of the totality, if you're interested in checking it out. A number of us here have already made our plans. If you haven't made your plans yet, it's probably too late to find any place to stay along this line. I know that when I was checking for places to stay in January, they were already booked up. So I felt I was lucky in January to find a place. But, you know, maybe you've already made your plans or you know somebody that lives down there. But no need to fear. There is another one coming in April of 2024, and in this case, the totality runs right down the St. Lawrence River. So it's pretty sweet for us here in Ottawa. Just have an hour drive and we're right there. And so that's it. So like I said, I have examples of all that equipment on the table here if you want to look after. Otherwise, I don't think we have time for questions.
Yeah, I think we'll have to do that next slide.
Yeah, you can come see me after if you have any questions. Otherwise, thank you.
Okay, so next up, we're going to try to get this done really quickly here, but Brian wants to come up here and talk about the GA. So we'll have to do
Okay, very quickly. Yeah, thank you, everybody. Listen, we're 20 months into the programming and planning for this General Assembly. We're 28 days out. Before Paul started his talk, we were 29 days out. All right. Anyway, listen, people have come forward with lots of great ideas. Tim and I have been working night and day on this stuff. It's been crazy. We haven't been able to incorporate everything. We've done our best with everything. We've got about 145 people registered for the GA right now, about 60 from the Ottawa Centre. We're hoping we've got one more week of registration to go. Please go online if you want to book just for the banquet on the Sunday evening. Please go ahead and do that. But I want to say thank you. If you have something that you've put your name down for at the silent auction, our fundraiser there, please come and give us your money for that. And special thanks to Rick and Jeanette Wagner who gave us a nice gift baskets over there. All right, so all of the Ottawa Centre Council, Executive, National Council reps, all of the officials in the Centre have registered for the GA, so I hope you'll be able to join us. And 28 days to go. Next time I see you, it'll be at the GA, so let's roll it, Chris. And this is the last time we're going to see this, I guess. So this is how we started. This is how we started.
Thanks, Brian. Okay, so Gordon is going to take it from here for the star parties and stuff.
Okay, I'll be quick, really quick. FLO, we had our first star party, members only star party last weekend. It was great. Those of you who weren't there, you really missed something. Those of you who were there know how good it was. Partway into the evening, we got the aurora, and we decided to do a mini group photo. That's just some of the people that were there. We had about 20 people there, I think. Really good time. Next one is on the 24th of June, and that's new moon, so you should be there. Work parties, we're having work parties starting one tomorrow, one Sunday. If you can make it, please let me know ahead of time. Tomorrow
the work party. I know there are 2 people going for sure. Sunday, we're still waiting to see on the weather. So if you're thinking you can come Sunday, send me an email. I'll let you know if it's on or not. We'll have another work party next weekend and probably the weekend after. We do need volunteers, okay? We won't overwork you, and you'll get a lot of satisfaction out of it, okay? What's showing in the background here are some of the slides, I think, from last weekend's solar observing. Mike was going to present this, and he sent an email with his notes. He wanted to thank everybody who volunteered. And those of you who didn't volunteer, he wanted me to tell you you should volunteer. I'm paraphrasing. He also, I guess we had about 1,500 people at the height of the thing. Also, we're looking for coordinators, Star Party coordinator, members only event coordinator, outreach coordinators. I encourage you to get involved. You can contact Tim or Mike or me or Chris. And I think that's it. Did I miss anything, Chris?
Carp Star Party.
Carp Star Party.
Just follow the slides now.
Oh, I got to turn around to do that and think. Yeah, so there's Carp Star Party, which is the 16th, with the rain date on the 17th.
Slides coming. Just advance the slides.
Oh. Center button, left, right button.
Right.
Okay, so there's the Carp Star Party. Quick with your photo. Okay. And there are the primaries. Okay. And we also have one on the 30th, which is a tie-in with the GA. The Cube Gallery. When is that? Oh, July 6th and 7th, which is our next meeting. So. It's doing it magically.
I'll take it from here.
You'll take it from there? Thank you very much.
Thanks, Brian. Okay, so just to wrap it up here, Estelle's pick of the month is the one that spoke right here, in the brochure after the meeting. Membership fees, if you want to join the group, there are many benefits. You can rent a telescope out, you can access the observatories. There should be a long list of benefits coming up here, I think. Maybe not. These are the people here if you want to contact us for more information. I'm not sure if Eric was recording this here tonight from this little camera here. If he is, this is where you'd be able to stream or to watch the presentations all over again. And so this is our calendar of all the meetings. We had 114 people here tonight. Thank you very much for coming out. Thank you very much for all the speakers who came out there. I know we had a really tight agenda. I guess this is my first time doing this. Maybe I was a little ambitious, but to everyone who came up here and had a chance to speak, thank you so very much. Terrace, I'm sure we'll hear from you another time. I'll grab you some beers tonight. And next month, we'll have our meeting on July 7th. Until then, clear skies. And I guess we have the door prize too.